more topic I want to talk about in this chapter, and that's kinetic versus thermodynamic control. And this really won't come up a whole lot this semester, but it's a good way to kind of think about the difference between them. Remember, kinetics has to do with the rates of our reaction. Thermodynamics has to do with the energy or the stability of my reaction. So I could have a reactant, let's say A, and it forms two different products, and you will see this in 236, and we're going to say one of those products forms faster, but the other product is more stable. So which one ends up being our major product? How can we tweak our conditions to get one versus the other? So I'm going to have A going to B plus C, and then let's make some assumptions. Let's assume that B forms faster than a C. So what that means is the activation energy for B is less than that of C, right? Remember, the smaller our activation energy, the faster the reaction. So my activation energy for B is less than my activation energy for C, right? B has the smaller activation energy. And then we're going to assume that C is more stable than B. So C has a lower energy. Right? Remember, the lower in energy it is, the more stable it is. So one forms faster, but the other one is more stable. If we were to draw, we could draw an energy diagram and put both of them on there. So energy, my reaction, and let's use green for one of them. So I'm going to go up, and then I'm going to come back down. And we'll make this one C because I came down so far, it's pretty stable. And then we'll use purple for the other. They're both starting out as the same reactant, so I'm going to start out in the same spot. B is going to have a smaller activation energy, so I'm not going to go up as far. But then it's less stable, so it's going to be higher in energy when I finish. So this was B. This is C. And then A is my reactant for both of those. So if I was to look at my activation energy, I'm going to put them on here, but then probably take them off because it's going to get kind of messy, right? This is my activation energy for B. And then, I need to put some lines on my paper so I can draw straight ones. This would be my activation energy for C, right? So my activation energy for B is smaller than C. So B is going to form faster than C does. But then if I look at my free energy changes, right? C is more stable than B is. So this is my free energy change for B. This is my free energy change for C. So C is lower in energy, it's more stable, but it takes longer to form. B is higher in energy, it's not as stable as C, still more stable than B, right? It's still spontaneous, it's still going in the forward direction, but it's going to form faster. So essentially, which one is it going to make, right? Well, it depends on my reaction conditions. So at high temperatures, remember we can add heat to reactions. So at high temperatures, and remember heat or temperature is a measure of the average kinetic energy. So if I'm adding heat to it, right, I'm increasing its energy. So at high temperatures, I have enough energy to overcome that high activation energy. So even though I have to put more energy into it, because I'm at a high temperature, I have that energy. So at high temperatures, enough energy has been supplied to overcome that high activation energy. And my more stable product is going to be the predominant product. So at high temperatures, enough energy, right? Remember, temperature is a measure of average kinetic energy. So enough energy has been supplied to overcome the larger activation energy, right? We can overcome large energy barriers. We also have enough energy, probably, if the temperature is high enough, to go backwards, right? If we look at the back in the reverse direction, I said I would get some of this out of here because it's kind of messy, but if I'm going in the reverse direction, now C is my reactant, and my activation energy to go backwards is much bigger, right? It's between here and here. Like, that's a pretty big activation energy, but that's what my activation energy would be in the reverse direction. And if I have a high enough temperature, I would have enough energy to do that. It would still be non-spontaneous in that direction, but the reaction would be reversible, right? Not all reactions go in both directions. So enough energy has been supplied to overcome the larger activation energy. Likely also has enough energy to go in the reverse direction, right? My activation energy is much larger in that reverse direction, right? So we can go from products back to reactants. So it would be a reversible reaction. We could reach equilibrium. Equilibrium is going to be favored in the forward direction, right? Because that's the way that's going to give me the negative free energy change, right? It's more stable in that direction. C is the predominant product. It doesn't mean that I'm not going to make some B. I will, but it's going to be mostly C. So C is the predominant product. We always want to make the more stable one if we can. So it doesn't matter that it forms slower, has a higher activation energy. We have enough energy, right? If we have enough energy to get over that barrier, then the barrier is not much of a barrier, right? So C is the predominant product in this case. We could say since it's more stable and we can get there, right? We have enough energy to form it. So this would be considered thermodynamic control because we're making the thermodynamic favorable product, right? Remember, the faster one, kinetics has to do with speed, thermodynamics has to do with stability, right? It has to do with energy changes. So if we're going to form the one that's lower in energy, the one that's more stable, this is going to be thermodynamic control. So vigorous conditions, so high temperatures, that sort of thing, they tend to be reversible, and the major product is generally the more stable product. So vigorous conditions, so we're adding heat to it, tends to be reversible. The way I drew it, the forward direction is the favored one, but it can go in both directions. And the major product is the more stable product. And then at lower temperatures, as you can imagine, it's going to be the opposite, right? At lower temperatures, I don't have enough energy to overcome high activation energies. It's generally not going to be reversible because I don't have enough energy to go back, right? If I can't get over the bigger hump in the forward direction, I'm certainly not going to get over the even larger energy barrier in the reverse direction. And B is going to be my predominant product. And that's going to be kinetic control. So at low temperatures, not enough energy has been supplied to overcome large activation energies. Tends to be irreversible. And then B is the predominant product. So kinetic control. Right, so essentially mild conditions, not super high temperatures. It tends to be irreversible. The major product is the one that forms faster. So mild conditions, irreversible, and then the major product is the one that forms faster. It's the faster forming one. And like I said originally, we're not going to really have to choose between these. I'm not going to give us a reactant where we get two different products and say which is a thermodynamically controlled one and a kinetically controlled one. In 236, you will have to think about this. One of the reactions you're going to see in 236 is you're going to have a conjugated diene. So what that means is I have multiple double bonds and then they're alternating. So I have double, single, double. If you were to do this, it's actually not conjugated because they're not alternating, right? I have double, single, single, double. So alternating multiple and single bonds means they're conjugated. And if we were to add HX to it, again, X is a halogen, we can get a couple different products. So what I can do is I'm doing an addition reaction. This is very similar to what we were doing earlier, right? Remember when I had this and then I added HCl to it? We ended up doing that mechanism where we had that intermediate and then our halogen added. That's what we're doing here, right? I'm using my double bond on this side. I'm putting my halogen here, my hydrogen over here. So an addition reaction. However, the intermediate, when I did this one, I would have gone through this as an intermediate, and this intermediate has resonance. Resonance is not going away. So now my halogen can actually add to that carbon. So I end up with this product also. And for reasons that we haven't covered yet, but we will cover in this chapter, this is actually more stable. So this reaction, you get both of them, but at higher temperatures, this product is going to be the one that's you get most of. At lower temperatures, this is going to be the one that you get more of. That's my kinetically controlled product. And again, you won't have to choose here or this semester. It's just that it's a really good way to make sure that you have the difference between kinetics and thermodynamics, kind of everything straight in your head, right? Thermodynamics, we're talking about which is more stable. When we're talking about stability, we're talking about our energy, right? So in this case, C is more stable than B because it's lower in energy. If we're talking about how quickly something forms, we're talking about its activation energy. So B forms faster than C because it has lower energy. And then the one that forms faster doesn't have to be the one that's more stable, right? In this case, it's not. Sometimes it is, and then you don't have to choose because it's perfect in every way. But just to kind of start thinking about these and getting everything all kind of straight in your head, it's a good way to kind of compare and contrast energy changes and the rates of our reactions.